This is a quick video of exam number 3 review. This is not an exercise that you need to turn in. These are just additional problems that you could use in preparation for exam number 3. So you don't have to work these out. It's completely optional. We did problems number 1, 2, and 3 and some of these other ones during class, so I'm not going to do them now. I'm just going to focus on the ones that we did not cover. Problem number 7, you need a diode, resistor, and filter capacitor to convert AC to DC. In fact, it's just really a capacitor. The word filter means that it has a rather large capacitance, so it can actually smooth out that halfway rectified signal that you would get from a diode and resistor. The problem's solutions for these are 0 and then 10 volts divided by 2.7 kilo ohms. 10 volts, 0 amps, and 0 amps, and 0 amps over here. Let me show you why those are the answers. You might notice that this is an old paper in which the last number here is actually the new book and this is the old book. So this is a document from 3 years ago, the same review sheet I used back then. At that time, only a few people had the new edition and most people had the old edition. In this semester, the situation is reversed. 10.36 looks like this. So why is the answer 0 for the voltage? Let me see if I can show you why. This is an ideal diode, so this behaves like a conductor. So there's an IR drop, voltage drop across this. This behaves like a wire, and because wires have 0 resistance in this ideal situation, the voltage drop across the diode is therefore 0. And therefore, in order to figure out what the current is, you take the voltage drop across the resistor, which turns out to be 10 volts because there's no drop here, and then divided by the 2.7 kilo ohms to get the current. In the second problem, now we have the diode in the reverse bias condition, so there's no current, so that's why the current is 0 in this problem. And if the current is 0, then there's no voltage drop across here, so that means that if you have 10 volts from here to here, if there's no current, if there's no voltage drop here, then it has to be all across the diode, and that's why this voltage here is 10 volts. Notice that this plus and minus sign, what that means is that this is where you put the red wire and the black wire for your from your multimeter. On this last problem, you have 10 volts here and ground down here. Since we have this in the forward biased direction over here, it's going to be pretty much a short to ground. Electrons are going to choose not to go through that branch because they have a short circuit path to ground. And that means that if you have a short here, that's going to be 0, so that's why the current is 0. And also, since this is forward bias, acting like a wire, the voltage drop across this is 0. So it's not that, you know, this is the current through this one is 0, because it's not. It's the current through this branch that's 0, and the voltage drop across that diode is 0. In problem number 9, you have a function generator, Zener diode, and a resistor. And the way that it breaks down is that across the resistor, you have pretty much the top of this little part right here. It says in the problem that you have a 0.7 volt drop for the forward bias condition. So here's the diode plot. Forward biased, it goes only up to 0.7 right there. And then the rest of it is the rest of the drop is across the resistor. So this plus this has to give you that. In the reverse bias condition, you have no current flowing through this guy here, so that's why you have no voltage for a length of time until you reach or exceed the Zener voltage, in which case the Zener diode becomes conductive and you start to get this right here. Basically, you can look at the Zener voltage, which is 5 volts, and that's what is going to be clipped off at the bottom of this sine wave. So if you take this plus this, you're going to get the bottom of that sine wave. On the last page, problem number 1 on the back. This is problem 45 in the new book in chapter 13. What you want to do is take a path from the 10 volts all the way to ground, I'm going to choose the path that involves going from the emitter to the base, because that is what's given in the problem. They tell you that the base emitter voltage is 0.7, like we had seen in a previous problem. They also tell you that beta is 100. So looking at the way the signs fall here, it's a positive here and a negative right there, and that's 0.7 volts from the emitter to the base. So it's positive voltage there relative to negative right here. So if you write this, so this is a path that you can take and actually know what the drops are for this forward bias region of the transistor. So you start at 10 volts, so that's what I have here. You have a drop of 0.7, that's what I have next. And then this current that's coming out of here is I sub B times the resistance. So I sub B times the resistance gives me 0 volts down here at the bottom. This is, maybe I can just clearly make it more clear about which way the direction the currents are flowing. The leg with the arrow is always the emitter, and that's I sub E. And I sub E should always work out in such a way that it's, can't see from the reflection really, can you? Not really very well. I sub C plus I sub B. So that means that I sub C is right there, and it has to be leaving. I sub B has to be leaving, so these two have to add up. These two have to be add up to be this one over here because of this equation right there. That means that there's a positive here and a negative there. That's why I have a drop of minus IB. The only unknown in this equation is IB. That will allow me to solve for it and put it right here. If I then use the beta that was given in the problem of 100, I can use that to find I sub C. I sub C would then go right here. I would use this equation that IE is equal to IC plus IB to figure out what that is. So that would go right over here. And I could use the definition of alpha, which is IC over IE, and that number would go right here. To find capital I and capital V, I go back to my drawing and realize that capital I is the same as IC. So whatever answer you put right here would also go over there. And for the voltage drop from there to there, we know that this is 0. We know the current through this. We know the resistance there. An IR drop would tell us what the voltage is. And the drop across here, and if this is 0, it would tell us, if we're going this direction, for example, what the rise would be. So this is basically the 2.2 kilo ohms times the collector current.